You've used ChatGPT. You've asked it questions, gotten answers, maybe even had it write you an email or two. It works. But here's something most people don't know: the raw model underneath ChatGPT is almost completely useless out of the box. If you took the base model, the thing trained on the entire internet, and asked it a question, it wouldn't answer. It would just try to complete your sentence, like autocomplete on steroids. It has no concept of being helpful, no sense of what's appropriate, no idea that it should refuse dangerous requests. It's just a prediction machine. So how does it go from that, a raw text predictor, to the assistant you actually use? The answer is fine-tuning, and that's what we're covering today. By the end of this video, you'll understand the 3 key steps that turn a general model into a specialist, and you'll know why this is the most important idea in AI right now. Think of a language model like a person who has read every book in the library but never spoken to another human being. They know an enormous amount, but they don't know how to have a conversation. They don't know when to be formal or casual. They don't know that some questions shouldn't be answered. That person has knowledge but no social skills. A base language model is the same thing. It's been trained on billions of web pages, books, and articles. It knows what words tend to follow other words. But it's never been taught how to be useful. Training an AI happens in 2 distinct phases. Phase 1 is pre-training. The model reads the internet, learning patterns of language. This takes months, costs millions of dollars, and requires massive data centers full of specialized chips. Nobody does this in their garage. Phase 2 is fine-tuning, teaching the pre-trained model how to actually help people. This takes hours or days, costs anywhere from $10 to a few $1,000s, and you can do it on a single powerful computer. The same model architecture, a completely different purpose. Pre-training gives the model knowledge. Fine-tuning gives it behavior. The first and most important step is called Supervised Fine-Tuning, or SFT for short. Despite the technical name, the idea is simple: you show the model examples of what good answers look like. Here's how it works. You create a dataset of prompts and the ideal responses. Maybe a few thousand examples. For each one, you write the question and the perfect answer. Then you train the model on these pairs, the same way you train it on raw text during pre-training, but now it's learning the pattern of question followed by helpful answer, instead of just word followed by next word. It's like giving a brilliant but socially awkward person a handbook of conversation examples. When someone says hello, you say hello back. When someone asks for help, you offer a solution. When someone asks you to do something dangerous, you politely decline. After enough examples, the patterns stick. This one step alone transforms the model's behavior dramatically. A model that's gone through SFT can follow instructions, answer questions, and refuse inappropriate requests. The knowledge was always there, fine-tuning just taught the model how to use it. But supervised fine-tuning has a limitation. The model learns to imitate the examples, but it doesn't know which of its answers are better than others. If you showed it good examples, great. But what if it generates something mediocre? How do you tell it, that one was okay, but this one is better? This is where preference alignment comes in. The 2 main approaches are called reinforcement learning from human feedback, an absolute mouthful usually shortened to RLHF, and a newer, simpler method called direct preference optimization, or DPO. Both work on the same principle. You show the model 2 different answers to the same question. A human, or sometimes another AI, picks which one is better. The model learns not just what to say, but what kind of response people actually prefer. This is why ChatGPT doesn't give you dangerous instructions when you ask. It's why it tries to be concise when you want a quick answer and detailed when you're learning something new. The base model knows all the possible answers. Preference alignment teaches it which ones to pick. And here's the really elegant part. This step doesn't require the model to learn anything new about the world. It already knows everything it needs to know. It just needs to learn what humans value. Same knowledge, better judgment. So what actually changes inside the model during fine-tuning? The answer might surprise you: not that much. A language model stores everything it knows in numbers called weights or parameters. GPT 5.5 has over 1 trillion of them. During fine-tuning, almost all of these numbers shift a tiny bit. But certain layers, the parts of the model closest to the output, tend to change the most. The model keeps its core knowledge. It still knows that Paris is the capital of France. It still understands grammar and logic and all the facts it learned during pre-training. What changes is which parts of that knowledge get activated when you ask a question. Think of it like adjusting the dials on a mixing board. All the instruments are already there, the drums, the guitar, the vocals. Fine-tuning is just turning some channels up and others down until the mix sounds right. This is why fine-tuning is so efficient compared to pre-training. You're not teaching the model anything new. You're just teaching it how to behave with the knowledge it already has. Now here's the part that actually matters for you watching this. A few years ago, fine-tuning a model required the same kind of computing power as pre-training, out of reach for almost everyone. Today, that's no longer true. A technique called LoRA, low-rank adaptation, changed everything. Instead of updating all the model's parameters, LoRA adds a small set of new parameters and only trains those. The original model stays frozen. The result is that you can fine-tune a powerful open model on a single graphics card. Not a data center, not a cluster, one good GPU. And with quantized LoRA, or QLoRA for short, you can do it with even less. A model that normally needs 24 GB of memory can be fine-tuned with just 8 or 10. That's a consumer laptop. Tools like Unsloth and Axolotl wrap all of this into simple commands. You pick a base model. You prepare your examples. You run one command. Hours later, you have a custom AI specialized for your exact task. The barrier to entry has collapsed. If you have 100 good examples of what you want the model to do, you can fine-tune it this weekend. Let's bring this together. Every capable AI assistant you've ever used went through the same 3 steps. Pre-training to absorb knowledge. Supervised fine-tuning to learn how to respond. Preference alignment to learn what good responses look like. The model that reads the entire internet is impressive but useless. The model that follows instructions is useful. The model that knows what you value feels almost human. And here's the one thing I want you to take away. Fine-tuning is not reserved for researchers at big labs anymore. Open models are getting better every month. The tools are free. The compute costs less than a nice dinner. If you've ever wanted an AI that does exactly what you need, the way you want it done, you can build that. Starting this weekend. Next episode, we're going to look at the other side of specialization, Retrieval Augmented Generation, or RAG. How to give a model access to your own documents and data without fine-tuning at all. 2 different paths to the same goal. Subscribe so you don't miss it.